Okay, so first and foremost, just a few quick announcements. I have created a Google Classroom just so that we can manage everything. I sent all of you invitations. I think Nuwan and Hasini have accepted it. So you guys can accept it as well. And it's pretty straightforward. There's a section called classwork. When you go there, you can see all the weeks. It's pretty much like fields essentially. And basically what I'll do is the recordings, I'll put it up here, right? So basically Monday's session is here, the recording, right? And I've given a small overview of what is covered. Also, along with it, I've given important materials. So for example, the ROS tutorials, the MATLAB sort of code for ROS, plus I put this PDF basically here that covers what I basically did last time, right? So last time I gave everyone an introduction to the concepts of ROS, and then I also just did a simple example where we downloaded some code from GitHub, USB camera code, and then we built it, and then we tried to access the information coming from a USB camera, right? So all that information is here. So you can set it up by yourself. Also, basically the code that I used to connect it to MATLAB and write a simple subscriber, that's here as well. Right, so my plan is to basically try to do a combination of theory and then practical, small practical things like this, right? So till next week, I'll just be mainly using MATLAB, and then from next week onwards, we'll start using Python. So the reason I want to start with MATLAB is because that's what I think most of us are familiar with. So because I don't want to confuse the ROS concepts with the programming concepts, right? Because those are two different things. So I'm just using MATLAB to explain the ROS concepts, things like subscribers, publishers, things like that, right? And then it's the same concepts being used with a different programming language like Python or C++, right? So I think we'll mostly use Python because it's a little bit more easier than C++. But if you all are interested in doing everything in C++, you can do that in C++ as well, right? So this PDF will cover basically what we did last week, right? So we are still in week 1, and today I'm going to start on a very theoretical part of what we're doing, which is probabilistic robotics, right? So basically everything that we'll be covering has to do with probability, right? The reason for this is, can someone actually tell me why probability and statistics are important when it comes to robotics? Any ideas? Also, if any of you can have your videos on, it will be good, then we can actually interact with you all. Only if you don't have any data problems or anything. So why is probability an important part in robotics? Or in engineering in general? Any others?
So you can say the rate of success.
Okay. What else? Yeah, that's important. No one answering something?
We are always dealing with the data. I mean, the sensor data.
Yeah, that's correct, right? So the both of your answers are correct to a certain extent. So the issue is, now we are used to what we call deterministic equations, right? Now, for example, if we say, I don't know, let's take a simple example like F equals ma or something, right? So once we plug in these values, we can get the force of the external force applying on an object, right? This is a deterministic relationship here. Whatever you plug in, you get the correct answer here. But in the real world, there's a lot of uncertainty, right? Everything is not perfect. So for example, whatever we are measuring, this acceleration or this mass, we'll need a sensor to measure it, right? So all sensors have noise. right? So no, like for example, if you use some sort of accelerometer, right? Accelerometer to measure the acceleration, you will get an answer. Let's say it's 5 meters per square second or something like that. But this answer is not the actual perfect value that we are used to when we are doing like in, when you're at school, when we plug in values to these equations, right? In the real world, this sensor value will actually be full of noise, right? Although we say 5 meters per square second, there'll be some sort of error associated with that, right? So when we are building complicated systems and complicated engineering systems, not just robotics, we need to start thinking about things that are non-deterministic, right? So these are called deterministic equations when everything is, straightforward, right? Where you don't have any uncertainty. But when you talk about non-deterministic systems, right? The word that we generally use to describe those systems is stochastic systems, right? So stochastic systems are systems with uncertainty, right? Deterministic systems have no uncertainty. So basically, no uncertainty. So most systems, like in complex engineering, are stochastic in nature, right? There's a lot of uncertainty. Even when we are talking about not just robotics, if you're talking about communication, if you're sending a SMS between one phone to another, right, and sending this message, again, there's a lot of uncertainty in how this signal is transmitting through the air, right? There's a lot of noise that can get added to the signal, right? So you don't have perfect signals anywhere, right? So in robotics, this is also the case, right? Because when you're dealing with real systems, right, like a robot, there are two aspects of this that become stochastic, right? One is, as Nuwan pointed out, sensor data, right? Sensors will have uncertainty. Another place where uncertainty happens is in the control signals, right? So for example, let's say our computer says move 5 meters, right? Will our motors actually move 5 meters all the time? No, right? Because there is again uncertainty and noise, right? So for example, let's say I tell this robot to move 5 meters. There's going to be slip in the wheels. There's going to be all sorts of other things that are not modeled by that simple equation, right? So all we can do in engineering is to try to understand this uncertainty as much as possible and try to model it into our systems, right? So that when we take into account the uncertainty, our answers can be better, right? We can't completely eliminate the uncertainty, right? We can't do that. All we can do is try and understand it a bit better and try to use the maths of like probability and statistics to help us model these systems better, right? So once we model the systems by taking into account these uncertainties, we can get better answers, right? And our systems will perform better than if we just assume that they're deterministic, but they're not, right? So these are all stochastic systems. Okay, so that's basically why we need to think about probabilistic robotics, right? And so before we actually get into some of the complicated like ideas in probabilistic robotics, what I'm going to do today, so today's lecture is basically going to be a revision of probability, right? So most of these things I'm going to cover today, all of you must know. Like I'm pretty sure all of you already know these things because we've learned probabilities in school time, right? And then we learn probability again in university. So most of these things we know, but what I'm going to do is just do a quick revision because that way we can all refresh our memory, right? I don't know about you guys. For me, something I learned 1 month ago, I already forget it, right? So things that we learned during school time and our undergrad, I'm sure all of us very easily can forget it, right? So what I'm going to do is just quickly go through some of the basic ideas so that we can refresh our memory, so that next week I will really get into the robotics parts, right? So today is just a bit of maths, right? So quick revision of ideas, right? And in the classroom, what I'll do is I'll add a textbook, and I'll give a chapter in that textbook that also does this sort of quick revision, so that you can, if you want, because we only have an hour, you can quickly go through that material again and try to remind yourselves. Another thing you can do is, if you have old notes that you have from university or school, just roughly read through it to get a quick refresher of probability, right? Okay, so we're just going to go through some basic concepts, and if there are anything that's confusing, please let me know, and I can sort of explain it a little bit better, right? So first and foremost is this concept of a random variable, right? So can someone tell me what a random variable is? By the way, it's okay if you can't remember, but just your feeling of what a random variable is. Okay, so let me just start off. Okay, so we are first going to start off by talking about not just any random variable. We're going to start off by talking about discrete random variables, right? So what is a discrete random variable? So random variable is just a variable that can capture probability, right? It's not like a normal numerical variable. Like for example, when we say x equals 5 or something like that, this is not a random variable, right? A random variable is a variable that encodes probabilistic information, right? So when we are dealing with robots, when we are talking about sensor information, the position of a robot, things like that, we typically use random variables to describe it, right? So basically how the way we would I'll explain this using a simple example, right? Let's talk about the classic probability example. Let's say flipping a coin, right? Flipping a coin. So what we would do is we can define a random variable for the outcome of the coin, right? So we can say x is the outcome of the coin flip, right? So we know that the coin can be either heads or tails. So how we would express this random, so x is the random variable. We can define any sort of probabilistic event using a random variable, right? So here we've defined the outcome of a coin flip as a random variable x, right? So how you usually, the notation you use to describe this is, so for example, let's say I want to find the probability of heads, then what I would say is x equals heads. Like what's the probability of x equals heads, and then I would say that's 0.5, and what's the probability of x equals tails, okay? And that's the probability of 0.5, right? So this is an example of flipping a coin. All right, so here I think just very quickly the notation is important, right? So when we talk about the notation of using random variables, how we usually do it is like this, right? So this is the random variable, and then the simple x is essentially the event, particular, like specific event, right? So what's the probability that my outcome of the coin flip is heads? That's what this probability is telling us, right? So px of x. Another way this is abbreviated usually is, instead of writing x equals x, sometimes they straight away write p of simple x like this, right? This both means the same thing, right? So whatever notation you can use, but when you see this in typical textbooks and things like that, you can use either notation, right? Okay, so is that clear so far? By the way, I might be covering things we all know. Like I'll get into a bit more complicated stuff, but I think we should start from the foundations and build up little by little, right? Okay, so in this case, flipping a coin is what we call a discrete random variable, right? Because it has discrete events, right? So x can take, if we take it as a set, it can take heads or tails, right? It's discrete values. It's not continuous values, right? So if we were to plot this probability, p of x equals simple x, right? with the event, with the random variable x, what we will get is a graph like this, right? So we'll have both events, heads and tails, and we will have 0.5 and 0.5. So you can see here from this graph itself that this is very discrete. Right? Another thing you can do is you can even represent heads and tails as numbers, right? So for example, you can say heads is 1 and tails is 0, right? So you're essentially then asking what's the probability of x equaling 1 and x equaling 0, right? So the advantage of having a random variable is you can encode numbers into it, right? So you don't have to write heads and tails. You can start putting, in this case, discrete numbers, right? In continuous case, you can have continuous numbers representing the different outcomes, right? So in heads and tails, you can just represent it as like 1 or 0, right? So this is kind of a binary kind of situation that we are seeing, right? Also, this distribution, right, Px equals simple x, is called a probability mass distribution. Right? And this is called a probability mass function. Right? So it's a probability mass function in the case where it's discrete. Right? So remember we're dealing with discrete random variables. So when you take this distribution P capital X, the random variable equaling some sort of event, the whole function of it, right, which is given by this graph, we call that a probability mass function or probability mass distribution. Okay, so another important thing is that the sum of, let's say in this case, since it's discrete, we are dealing with the sum of all the events, right, equals 1, right? So you can see here 0.5 plus 0.5 will be equal to 1, right? Because these events represent all the possibilities that can occur, right? So if I sum up all the probabilities of what could occur, it should be equal to 1, right? Because probability is kind of like it's essentially a percentage, right? Like what Smith said before, like basically some sort of like percentage of the likelihood of something happening, right? Okay, so that's about discrete random variables. Before we go any further, any questions? By the way, these are probably maybe covering 2 basic things, but I think it will be, I'm slowly going to build up. So by the end of the class, it will be a bit more complicated, but hopefully everyone can follow so far, right? Okay, so that's discrete random variables. Now we'll talk about continuous random variables. Continuous random variables. So continuous random variables are similar to discrete, but now we have continuous spectrum, right? So for example, let's take I don't know, height, right, of let's say a class, right? So let's take all of us, right? Like we will have different heights, and these different heights can be continuous, right? It doesn't have to be discrete values, right? So there'll be a continuous probability associated with our heights, right? So for example, let's say probability, so we have to define what our random variable is going to be, right? So we say x is basically the random variable of so we have to define some sort of event, right? So picking someone with a particular height. Or yeah, you can do it, right? So x can be that event, right? So so then, for example, we can ask, what's the probability that I will pick someone who is of height? Okay, so the thing about continuous random variables is it's difficult for us to pinpoint a particular value because it's continuous. So what usually happens is you have to pick between a range, right? So for example, I would pick usually ask it, what's the probability that I will pick someone whose height is less than, say, 1.5 meters, right? Or what's the probability that I will pick someone who is between 1 meter and 2 meter, right? Something like that, right? So typically when you're talking about continuous random variables, it's hard to specifically say who you're picking. So we always deal with particular ranges, right? So similar to having a probability mass distribution, what we have when we deal with probability distributions is something called a probability density function, right? Which is given by this, right? P of x. So the probability density function is so when we are dealing with discrete, we call it a probability mass function. When we are dealing with continuous, we call it a probability density function, and we also have the associated distribution, right? So here, like if you're still dealing with this example of height, so there are commonly found probability distributions that pop up in the world naturally, right? So a classic example of this are Gaussian distributions, right? Gaussian distributions. So something like height would typically be a Gaussian distribution, right? So if we look at the height of all of us here, right, we'll have only a little people, like only a few people who are really tall, and only a few people who are really short, right? Everyone will be kind of in the middle, right? So how our probability distribution, when we come talk about height, for example, will look like for the random variable x, right, will look something like this, right? So I'm trying to draw with my, right? So this is a Gaussian distribution, right? So the majority of people will say, let's say the average height is 1 point, I don't know, what's the average height? 1.2 meters? I don't know, I'm just guessing here, right? Most of the people will be somewhere in this average area, right? And there'll only be a few people who are really tall, like 2 meters tall or something like that, right? And a really few people who are, say, I don't know, 75 centimeters tall or something like that, right? So really short will only be a few people, really tall will be only a few people, but the majority of people will fall in this mid region, right? So Gaussian distributions are seen in lots of naturally occurring situations, right? Populations, right? For example, if you take your class exam marks, it will be distributed in a Gaussian distribution. Now, one cool advantage of Gaussian distributions is you can basically, so for example, this graph, the actual equation for it looks like this, right? So if I was to write the equation for this, it looks like this. Right? E to the power minus half. Okay, so this is basically, this equation gives you the shape of a graph, of this graph, right? By the way, this should be a bit more peaked than this, right? Actually draw better. It's really hard for me to draw, but I'm sure all of you have seen a Gaussian distribution, right? It should be a little peaked. So, okay, I'm terrible at drawing this, but you all have seen a Gaussian distribution. Let me just Google one also and show you. Right? So, point is this shape of the graph can be given by this equation, right? Another word for Gaussian distribution, you also refer to it as normal distributions, right? Sorry, my screen. Yeah, so this is what a Gaussian distribution typically looks like, right? So this equation gives you the shape of this distribution, right? And most of us have used those tables also that help us find actual probability values here, right? Like for example, if I want to find what's the probability that I'll find someone who is less than, say, 1.4 meters, what you do is you would take this probability distribution, find 1.4 meters, and you would integrate this area, and that will tell you what's the probability of finding someone less than 1.4 meters, right? And then you can, like I mentioned before, calculate those different ranges. Now the thing is, you can see here there are these two values here, right? One value is sigma and another value mu, right? Everything else you can like is straightforward. X is the random variable, like this variable over here. Sigma and mu essentially refer to the mean of the distribution and what we call the variance of the distribution, right? So the mean is typically this value over here, right? Peaks. Variance is essentially how spread out this graph is, right? So if it's very spread out, it has a high variance, right? That means the distribution is spread out, and if it has a very low variance, that means it's kind of peaking very close to values, right? So all the values are closer to the mean, right? So what the variance actually measures is how far away you are from how far away you're sort of distributed away from the mean, right? So I'm not going to go into the equations of how to calculate variance and mean. If you all have the notes from your former like undergrad or school stuff, you can go through how to calculate it. But I think all of us understand the meaning of mean and variance, right? So here you can see the only values that you need to explain a Gaussian distribution is just the mean and the variance, right? Because this equation, we already know this equation. So you can sort of explain a Gaussian distribution by just giving the mean and variance, right? So for example, if let's say Gihan asked me what's the Gaussian distribution of our sensor or something like that, all I have to give him is mu and sigma, right? I just have to tell him what the mean of my sensor is, like what's the average value, as well as what's the variance, like what's the noise, or like how far away is it distributed from that mean. And then he can plot this Gaussian distribution himself, right? So all we need are these two parameters, right? So Gaussian distribution is also referred to as a parametric distribution because it can, like this entire graph can be just summarized by mu and sigma, right? So that's something to also keep in mind. Another thing that's important when we're dealing with robotics is to understand that in most cases, now in this case, we have a single variable, right? And we have for example, let's say this height value, our mean will be 1.2 meters, right? And then our variance will also have a particular value. But in robotics and more complicated engineering situations, we will have multi-variable situations, right? So these graphs won't be 2D like this, it will be flat. It will be 3D and actually even higher dimensions than that, right? So if I show you a picture of a multi-variable Gaussian. So the reason we are focusing on Gaussians a lot is because they are very common in natural situations, right? Because it captures the naturally sort of distributed phenomenon, right? So here you can see what a multivariable Gaussian looks like, right? So in this case, it's three-dimensional. Sorry, yeah, three-dimensional. And then you can have like multivariable, Gaussian distributions like this. So in cases like this, multivariable Gaussians, right? Multivariable Gaussians. What we have is mu will be a vector. The mean will be a vector. And this variance, right, will be a matrix, right, called, actually we use the capital sigma for this. It's called a covariance matrix. So a multivariable Gaussian will look something like this, right? So if this was the single variable Gaussian distribution or multivariable Gaussian distribution, it will look like this. We have determinant. So when you're dealing with multivariable, you'll have matrices and vectors, essentially. So you'll have this sigma to the power minus half, and you'll have the exponent, right? And again minus, and half into, here you notice there was a square here, right? X minus mu squared over sigma squared. So that will be replaced by x minus mu transpose into sigma inverse x minus mu, like this, right? So you can see it's very similar to the previous single variable case, right? If I zoom out a little bit, right? It's very similar, but everything has been replaced by a matrix and a vector because we're dealing with multiple variables, right? So that is important in robotics because we'll be dealing with situations where we have multiple variables, right? So these two words are important to remember, like covariance matrix, and this will be the mean vector, right? The average vector. Okay, before we move any forward, any questions? Sorry, I've been talking a lot. Am I going too fast, or is this okay pace to be going in?
This is okay for me.
So by the way, this is just a quick revision. Nothing like, I hope it's not too intense. All right, so similar to the discrete random variable, in continuous random variables, if you sum the probability distribution, right? But in this case, it will be integral because it's continuous, right? You will get 1, and that's important. Okay, so that's about discrete random variables and continuous random variables about probability distribution. So this was just an example of a probability distribution, the Gaussian distribution. And it's a very important example because in robotic situations, you come across Gaussian distributions a lot, right? So just a basic understanding of their shape, these different parameters, like mean, covariance matrix, mean, and sigma and variance, those kind of things are important, right? Okay. Right. So now that we talked about continuous random variables and discrete random variables, now we'll talk a little bit about joint distributions. Joint distributions. So to understand joint distributions, I'm actually going to take a discrete value example to do this because it will be easier to understand. And for this, I'll actually need all of our help, right? So I know everyone is a bit shy to talk, but even if you can mention in the chat, it will be really helpful, right? So let's take a quick count. Let's talk about who here likes chocolate ice cream and vanilla ice cream, right? So let's say chocolate ice cream. Chocolate, and let's talk about vanilla ice cream, right? And chocolate ice cream. Okay, so what I'm going to do is we're going to just quickly, you guys can just mention what your favorite is, and I'm going to also divide this between male and female, right? And I'm trying to design a small distribution, and you will understand, just to help you understand the concept of joint distributions and all the other things that I want to talk about past that, right? So we have male, female, chocolate ice cream, vanilla ice cream. So essentially what we have here are two variables, right? Two random variables. One random variable, let's call X, is what ice cream flavor you like, right? And we can define another random variable Y, whether you're male or female, right? So quickly, can the guys, okay, can all of you tell me what your favorite is? Okay, so Jihan is chocolate. Just type in the chat really quickly, or tell me quickly, and then I can count how many. So far we have 1 for chocolate. Smith here is chocolate. Everyone else? Smith is chocolate. Okay, everyone is chocolate.
I like vanilla.
Okay, so no one likes vanilla. Udar? Okay, so let's assume Udara likes vanilla. And I'm also going to say I like vanilla. So we have three. So overall, we have three chocolates, right? And out of those chocolates, we had Dihan liking chocolate. So that's one chocolate. And then Hasini and Smithya likes chocolate. So they'll be going here. And as for vanilla ice cream, basically, Udara, are you here? I put you in vanilla. Okay, so let's actually say Udara likes chocolate. Fine, we'll have him like vanilla, right? So we have three males. By the way, is it Udara or Udara? It's Udara, right? It's a guy, right? I am sorry, I haven't met Udara.
Udar.
Ah, right. Udara, what do you like,
Udar.
Udara? Chocolate. Yeah, what do you like, Udara?
Everything,
Chocolate?
as you wish. Anything.
Anything. Okay. I'll put you as vanilla ice cream. Okay, so we have three. Okay, so here now we have a table, and we can actually sum this table up as well, right? So on this side, I'm going to put basically the summation here, right? And then we have 3 here, right? And if I sum this, I'll have 2 and 4, and the total here is 6, right? So this is a situation where we've basically sampled everyone's ice cream preferences, right? So this isn't a probability distribution yet, right? These are just the random variable values, right? So if I was to convert this into a probability distribution, it's quite simple. What I do is I divide everything by 6, right? Which is the total number. So if what I will get then is what's the probability of simple x, right? So I have chocolate and then vanilla. Change the colors, right? And then I have male, female, right? So this will be, on this side, it will be the probability of simple y, right? And again, we can draw a table, right? And how I will get the probability is I will divide this by 6, right? So we'll have, just quickly use MATLAB to do some maths, right? So what we'll have is 1/6, which is 0.616. And then we'll have twice of that, which is like 0.34, right? And then we have 3/6, which is 0.5, and then 0 here, right? So what we will get here in terms of totals is, this is like 0.33. And actually, let's stick to fractions because then it will be easy. We'll have 1/6 here, 2/6 here, right? 3/6 here, right? 0. And here now the totals add up to 1, right? And here we have 2/6 and 4/6, right? So this will be what we call a joint probability distribution. Because if I take this particular, let's take this event. What is this event telling me? This is the event, right? This is the probability that I'm getting someone who likes chocolate and, right, is female. Right, so this is what we call a joint probability, right? So the way we would write this mathematically is P, X, and Y. That's one way we write it. Another way we write it is P, we say X, Y like this as well, right? So all of these are different ways you can represent this joint probability, right? So this joint probability distribution is just simply this part, right? So these are the margins where I've added, these are the totals, right? So this is what we call the joint probability, and you can see if I add these joint probabilities, they reach 1. Right? So this itself is a probability distribution, P, X, and Y. That's how you would read it, right? What's the probability that you're a particular gender and you like a particular ice cream, right? So this is a joint probability. And then we have these totals. These totals also separately add up to 1. So this is the concept behind a joint probability, and this is the notation for it. Okay. The next thing we need to understand is, so that's joint probability. And then another thing we have to understand is this column here, right? If I take this column here, this is also probability distribution, right? This probability distribution tells you, it's essentially this, right? P of X, like the probability of ice cream, right? Whether someone likes chocolate ice cream or vanilla ice cream, right? So if I give a population, this will tell you what's the probability among us. Some of us will like chocolate and some of us will like vanilla, right? So this is what we call a marginal probability. Marginal probability. So this middle red color square is the joint probability, and this side is called the marginal probability. And you can see here the marginal probability is the sum of each of these rows, right? And this is also another marginal probability, this one over here. So by the way, this was this. This is another marginal probability, P of Y, right? And this tells you if I have the few of us, what's the probability if I randomly pick someone, there'll be male or female, right? So this captures, there's 6 of us and there are 4 guys and 2 girls, right? So you can see that this probability captures that probability, like P of Y, like what's the probability will be either male or female. And this marginal probability captures which of us would be likely to have chocolate, would likely to like chocolate or vanilla. But this middle one is what captures the combination of the two. Right? What's the joint probability of you liking chocolate as well as being a male or female? Okay, so this is a joint probability, right? So all of these individual things add up to 1. Right? So these are marginal, they're called marginal probabilities because they're in these margins here. Okay, so this is a case of a discrete situation, and I hope all of you can imagine what a continuous example of this would look like. So here we can also talk about something called conditional probability. Right? So this is joint probability, and it's basically what you need to know about joint probability. Now we'll talk about conditional probability, and we'll use the same example to talk about it, right? Conditional probability. So conditional probability is basically the question, given you're female, what's the probability you like chocolate, right? So for example, given you're female, what is the probability that you like a particular value, right? So for example, chocolate, given you're female. So given a certain information, what is the probability of something else, right? This can work the other way around as well. Given you, we have a bunch of people who like chocolate, what's the probability that you're a girl or a boy, right? So let's take this example, right? Given you're female, what's the probability that you like chocolate? So when I say given you're female, we have to look at only this column, right? So given you're female, so that's 2 over 6. Out of the people who are female, what is the probability that you like chocolate, right? So out of this pool of people, right, what is the probability that you like chocolate? So actually this might be a bad example because this will be equal to 1, right? Because all the girls here like chocolate. Let's actually take the other example, chocolate male, right? So given you're male, then we'll have to look at this column. What's the probability you like chocolate? So out of all the people who are male, that's 4 over 6. That's the total male, right? Out of all the men, how many of you like chocolate? 1 over 6. So you can see that will be 1/4, right? So 1/4 of the guys like chocolate. So that's clear, right? There were total 4 guys here, right? And 1 out of the 4, Gihan, like chocolate, right? So how you would write this? So this was the example, right? So how you would write this in a mathematical form is, what is this, right? This is the total of all the guys, right? P of y. And 1/6 is the joint event of a guy liking ice cream, right? So you can think of it like this. Out of all the guys, that's this whole lot, how many like chocolate, right? So if you just write this mathematically, what I'm saying is, out of the joint distribution of Pxy divided by Py, right, is my joint conditional probability. Right, so we can actually plug in these same values, right? What's the probability of it being chocolate and male is 1/6. What's the total probability of it being male? 4/6, and you get 1/4. Right. So the equation, and all of you must have seen this equation before, for conditional probability is given by this. Right. Okay. So that's about conditional probability. There's another equation for conditional probability that we can derive from this, which is that if I take, so Pxy is the same as Pyx, right? So using the same equation, I can write the conditional probability of y given x, which is Px, and from this, what I can do is I can rewrite this as Pyx is equal to Py given x into Px. And I can take this equation and plug in that value, right? So what happens is, you can also write Px given y as, I can basically replace Pxy here with this, hold on, yeah, this is y given x, right? This is a comma, sorry, a bracket. So Px given y can be written as Py given x divided by Py into Px. So this is another way you can write the conditional probability. Right? So I'll just replace this Px and y joint event by the inverse of this condition, right? If I want to find the probability of x given y, I can take the probability of y given x multiplied by Px and divide by Py, right? Okay, so this probability of Py in all these cases are the same, right? Like, what's the probability of a guy? This event of Py is the same, right? So what we can do is, typically this can be factored out as a normalizing factor, and I'll talk about that a little bit more in detail next time. Right. So these are some of the important stuff that you need to know. In addition to that, yeah, another thing we need to understand is this concept of independence. Also, I think I've zoomed in too low. So let me just do this. Yeah. Sorry. So the next concept you need to be aware of is independence. Right? So the idea behind independence is, if you have these kind of joint probabilities like this, are they actually connected with each other, right? Whether, say, being female and eating chocolate ice cream, and being male and liking vanilla ice cream, if there's a connection between the two, right, then we say that they're dependent with each other. And clearly here it's dependent, right? There are more girls who like 1 out of, like, the total number of girls like chocolate ice cream, right? So if we talk about whether two events are independent, we can think about a different example. So in this case, they are not independent, they are dependent. So independent example would be something like, first I roll a dice. So roll a dice, and then I flip a coin. Right? These two events are independent from each other, right? Just because I flip a coin or roll a dice, it doesn't affect the other, right? So if I roll a dice, I get 1 out of 6 chances. If I flip a coin, I get 1 out of 2 chances, right? So just because I say roll a dice and I get 5, that doesn't affect if I'll get a head or tails, right? So these two events are independent. So if I take independent events, the joint probability of those independent events can be found using this formula, px into py, right? So these two events are independent. Okay, so let me write that. So if two events are independent, the joint probability of them occurring is px into py. So let's take that example of the first you roll a dice and then you flip a coin. Right? So rolling a dice, you get 1/6 of a probability, and then rolling the dice, you get half of a probability. So if I asked you, what's the probability that you get a 2 when you roll the dice and a heads, what you would do is multiply these two, right? The probability that you will roll a particular number in the dice and flip a particular number in the coin will be just the multiplication of these two, because they're independent events. Right? So I hope that gives you sort of an intuitive understanding of independent. Another important thing of independence is if I take conditional probability, that's x given y, if x and y are independent, it doesn't matter what happens to y, right? So for example, if I say I got a heads, right? Given I have a heads, what's the value of my roll, right, of the dice? It doesn't matter because they're independent. One doesn't affect the other. So px given y will simply be equal to px. Is that clear, or is it confusing? So if the whole idea of conditional is one depends on the other, right? Given y, what's x, right? But if the two events are independent and they are not connected to each other, it doesn't matter what y is. We'll have to just look at what this event is. Okay, so that's all right, so that's pretty much it in terms of the quick revision. So on Monday, what I'm hoping to do is I'm going to talk about what we call the Bayes filter. Bayes filter, right? So the Bayes filter is using all this knowledge, you can basically build this filter that will help us estimate certain values. And this is not only important in robotics. So we use it a lot in robotics, but even if you learn economics, even if you learn biology and any other engineering field, this Bayes filter is very, very important. Right? So based on this probability knowledge, we'll develop what we call the Bayes filter. All right, so before we wrap up, I'll just quickly summarize the areas that we covered, right? So, and by the way, if anything I said, if I didn't explain it properly, you can check these topics through a textbook or something like that and just quickly read up about it, right? So first I covered discrete random variables, like what they are, probability mass distributions, things like that. Then we talked about continuous random variables, right, what they are and important information on that. Then we talked about, if I'm not mistaken, joint distributions. So joint probability distributions, right? That's when we have two events happening together, right? Or happening in sequence, but we want to understand what's the probability of one affecting the other and so on, right? So along with this, we talked about conditional probability. Right? So given a certain event, what's the probability something else happens, right? Like given you're a girl, what's the probability you like chocolate or vice versa, right? So that's conditional probability. And then we learned a couple of equations on that. And then we also learned about independent events. So if we have both of those, you eating chocolate and you being a girl, if they are not connected, then we say they're independent. But if they are connected, we say they are dependent on each other. So if they're independent, the joint probability can just be obtained by just multiplying the two events. But if they are, and also if they're independent, the conditional probability doesn't matter, right? One does not affect the other. Okay, so that's basically what we talked about. And hopefully this will give you a very quick revision of probability. And I hope it was understandable. Maybe I went too fast, I don't know, but we can wrap it up. Do you all have any questions?
Doesn't know.
Sure. Anything else, guys? Anyone else? All good? Okay, so what we'll do is we'll meet on Monday. Yes, Smithya was about to say something.
Oh, no, I was just gonna say that I'm good.
Okay. By the way, is this pace okay? Am I going too fast? Am I talking too much, or am I just?
This is okay for me.
It's okay.
This is fine. Yeah, this is this is a revision class. This is like, I mean, it was good for me.
Okay. All right. So I will put up on Google Classrooms. I will put a small textbook. So this textbook is considered like the Bible of robotics, right? So it's called Probabilistic Robotics, right? And I will put this textbook on the Google Classroom. And here, if you are interested in going through this material again, basically it's under chapter 2, right? So in chapter 2, these are like the basic concepts in probability. So it's like a quick revision of these important information. Also, if any of you are interested, before next class, you can read whole of chapter 2, right? And that's basically the material I'll be covering. So this textbook is kind of roughly what I'll be following. Obviously not everything. This textbook has like 640 pages or something like that. So I'll just be taking the important parts from this. So if basically that's the introduction chapter as well. If you all want to read the introduction chapter, that's also, it's just about 9 or 10 pages. It'll be good. But what I'm focusing on mostly is this part, the maths probability part for the next 2 to 3 classes. So reading this, and it's a really good textbook. It's written in very simple English, so it's really easy to understand. And also there might be parts that are difficult to understand, but you don't have to understand everything, right? Because first time I read this, I didn't understand a lot of things in it as well. So it's completely okay. But I think here and there are like most of it should be straightforward to understand. So even if there are small parts that you don't understand, it's completely fine. Like I don't also completely understand everything. But this book is really good in giving you the basic concepts and the important ideas. Right? Okay. So I'll attach this book under week 1, and we'll use this as like a textbook moving forward. Also, if there's any feedback now that we've done about 1 week of these sessions, please tell me now, and I'll try and change the style or the way I'm giving the material. So just let me know as we move forward what we can do to make it better. Okay, otherwise I'll be doing the same thing. Okay, so now you have a taste of what I'll be doing. So if you all have any feedback, please let me know, and then I can get better at how I do it. All right, thanks guys.
Okay.
If there's anything, I'll be
Yeah.
around for maybe 2 minutes.
Thank you.
Thanks.
Thank you.